I would like to welcome on stage the next speaker, and we're going to be talking about terrestrial laser scanning, and we're going to explore the boundaries between TLS and iPhone, and the differences, similarities, capabilities. So, ladies and gentlemen, let me welcome on stage a geospatial researcher and educator with deep insights into field tech, Rami Tamimi. Rami, please join me on stage. Give it up for him. Rami, welcome.
Appreciate it. Thank you.
Enjoy the spotlight.
How's everyone doing today?
Woo!
How's everyone doing today?
Woo!
We still didn't have lunch yet, so you can't be that quiet. For those of you who don't know who I am, my name is Rami Tamimi. I'm a professional surveyor, a geospatial researcher and educator, and a PhD student. I've been on this PhD journey for some time now, so hopefully we finish that up soon. So my presentation is very similar to what was mentioned, but actually I'm going to be exploring the mapping with iPhones and the multi-year accuracy assessment evolution that we have gone through as we've tested the iPhone for its mapping capabilities. Now, I know that's a very controversial topic, especially among surveyors. So to have a surveyor talk about it, I think is, well, I think it's interesting, right? Earlier this morning, we had asked a question about what's your job title, and number one was CEO, but I'm pretty sure number two was surveyor. So by show of hands, how many of you guys here are surveyors? All right, so we've got a large number of surveyors. That's amazing. I also noticed that 28% of people acknowledge that they have skills in surveying. I would beg to differ. I think most of you have more skills than you realize. And we're going to explore those skills by assessing accuracy of the iPhone throughout many years, and to show you that, hey, you know, we got to start somewhere. It's not going to be perfect the first time you check accuracy of a data set. It's going to evolve, and it's going to get better, and you're going to get new ideas. So these are some of the things that I do. Among them, I am the founder of the Survey School. It is an online education platform designed for workforce development and educating anyone that is trying to get into the field of surveying. We have over 100 students. We also have a large number of students outside of the United States, here in Europe and in Asia. And furthermore, YouTube is my biggest platform. I have over 150 videos, free education online about surveying. So you're welcome to check out those platforms after the presentation. So the big question is, should surveyors be using iPhones? Is it really a professional tool? Should we be measuring property corners like this and assessing boundary lines and writing legal descriptions like this? Is this something we should be doing? Well, perhaps. The real question is, how accurate can we get it? If we can get the iPhone to be accurate enough, and we're able to trust the data that comes out of it, why wouldn't we be able to do this? Sure, this is an AI-generated image, but maybe there's a future where this is actually a reality. You see, I picked up the iPhone in 2020 when Apple introduced the LiDAR sensor, right? This was the first year I started seeing some geospatial sensors on the iPhone. And I started to think to myself, why? Why are these sensors on here? And more importantly, can I use these sensors for geospatial mapping and for surveying? I have been on this rabbit hole now for 5 years, trying every new iPhone that comes out to see if I can improve the workflow, if I can see some improvement in these sensors, if this consumer device can actually replace, can it supplement, or can it actually be an alternative to many of the sensors that we see today? Sensors that can cost hundreds of thousands of dollars, an iPhone can cost about $1,000. And as I was developing the workflows for all of these experiments, I realized that there are 4 main components. Component 1 is the system. That's the iPhone Pro that I'm using. Every year there's a new one. Sometimes I do multiple experiments a year, but it's the same system that I'm experimenting with. Next is the environment. This is where I'm at. Is it an urban area? Is it a forested area? Is it an open field? These are all things that play factors into the way the sensors perform. And if that sensor doesn't perform well, how do you expect your data to be accurate? Next is the ground truth. What sensors am I using to validate the accuracy of my iPhone? This is extremely important, because if I don't have a sensor that's accurate, how am I going to test my iPhone's accuracy with an inaccurate ground truth data set? And finally, reporting on the relative and absolute accuracy. What's the difference between the two? How are they used? How do we know if the accuracy of the relative model is good, but if the absolute model isn't? We'll go over that. Okay. Let's talk about some sensor theory. I apologize, I'm an academic, so there's going to be some math involved. Okay. Let's start with inertial measurement units. I promise you I will not go crazy with the math here. But an inertial measurement unit, or an IMU, is used to calculate the orientation and position of your device. Now, by utilizing the rotation matrix, which is the change in position, you're able to then see at a various time where you are. Now, again, I won't break down this too deeply, but as time moves on and as we rotate our IMU, we're able to see the orientation from start to where we are. That's T, time. The positional estimation is how far did we move? Did I move this way? Did I move this way? Did I move fast, slow? Based off of this information, we're able to actually model where the IMU is. Next is georeferencing. Consider this your position of the phone translated based off of the scale factor, the rotation matrix, and the translation vector of your origin point, that's when you hit start to record your data, and projected into some coordinate system, whether that's UTM, or if you're in the United States, that's NAD83, whatever your client wants. It could be a local system. Georeferencing is critical for absolute accuracy. Next is the LiDAR range equation. This is the equation that we use to figure out the distance from your LiDAR sensor to your object. It's a very simple equation. It uses the distance of the object, the speed of light, because you're using light pulse to measure, and the time difference it takes for that pulse to return. Now, there's obviously more math involved if you have multi-return sensors, but for the sake of keeping this simple, that is how LiDAR works. And sensor fusion is the mechanism used to bring all of this together. By fusing all of these sensors together in real time, you are now collecting data that you can use to acquire information about your survey. Okay, I'm done with the math. Let's talk about how I did these experiments. 2020, picked up the iPhone 12 Pro, and this was a hot topic on LinkedIn. Everyone was talking about it. Everyone wanted to know, like, there's a LiDAR sensor. Can we use it? Can we actually collect data with it? Is it like a scanner? And it's only $1,000. Like, it can't be that good, right? So that's when I decided to take to YouTube and said, I'm going to make a video explaining how I would test the accuracy with my total station. So I started the survey by establishing an unknown point, by resectioning to another unknown point, and using those two distances, I established a local coordinate system. This local coordinate system merely is a line that goes straight north. So now I've got this relative local coordinate system set up. I'm going to measure something. I didn't know what to measure. So I found a curb next to my condo and decided I'm going to measure this. This is not my twin brother. This is just clever editing. After taking the ground truth model, I then scanned with my iPhone. I used the 3D scanner app. The Land brothers had developed this app for fun, mind you, for fun. And they have millions of users now. They don't charge for it, and they can extract point clouds and all sorts of deliverables. So I took this point cloud that I just generated, and I brought it into AutoCAD Civil 3D. It's the software I'm used to using in surveying. And I decided I'm going to try to map out the feature. So I used the grading elevations to figure out where the low point and the high point of the curb were, and I simply just pulled the curb and gutter data. A couple of points, nothing crazy. I didn't really know what I was doing. But that was the first test I ever did of the iPhone. And that video got over 700,000 views. So this broke me into the rabbit hole that I'm in right now, which is trying to figure out how accurate I can get this iPhone to be. Okay, next year, 2021. New iPhone comes out, second generation. I'm excited, I buy it. I've never bought a new phone before. I used my wife's phone, actually, for the year before. But this year, I actually bought my own phone to be able to make this video. And I decided I'm going to do more than just a curve. I'm going to do this little island in front of my parents' house. I got a comment that also said, why are you using a 2-meter pole? You should be using a short pole. So naturally, I took the feedback and went and bought this small little pole and decided to try to use it, right? Okay, why not? So I measured a bunch of random features. Edge of sidewalk, manholes, PK nails, whatever I could. Just put some random things in there, measure it, and let's see what we can get when we scan it with the iPhone. Again, use the 3D scanner app, started to play with the manual settings a little bit, tried to get some more accurate scanning done. And I generated this little model. Brought it into Civil 3D, extracted the points. All right, I've got my model for the iPhone 13 Pro. I promise we'll go over results at the end. Like, don't worry, there will be numbers. Okay, next year comes, iPhone 14 Pro. I'm super excited because now I'm working with Leica. Thank you, Leica, for sending me an MS60. It's a half-second angular accurate total station. This thing's a beast. One of the comments I'd gotten was, you should be really testing a longer distance, just a linear distance to see how much drift there is in the data. So I did just that. I measured 100 feet. I placed a target on every 10-foot interval, and then I measured it with the total station to get my ground truth data. Additionally, I decided I want to test the iPhone 13 Pro with the iPhone 14 Pro. So I scanned a little park, playground thing, just to see how the reconstruction is, how the accuracy is, just to kind of do some more testing than just one little scan. What I found was the iPhone 14 Pro created more vertices than the iPhone 13 Pro. Different LiDAR sensor, slightly more upgraded. I wasn't a sensor guy yet. I was just trying to figure out accuracy for the system. Okay, iPhone 15 Pro. I'm going to go a little bit fast here because I'm short on time. iPhone 15 Pro comes out. What are we going to do? Well, we're going to measure this island, and then I'm going to take a GNSS receiver and establish geodetic coordinates. Now I'm going to ground truth my data to geodetic coordinates so that I can measure the absolute accuracy. I then brought my total station in, imported the geodetic coordinates, did a grid to ground conversion, and began acquiring with a TS16, slightly less precise, but still very accurate total station. And the last iPhone that came out was an iPhone 16 Pro. I decided to survey an entire building. Went all the way around the building, measured the curbs, the gutters, the building corners, as much information as I could, and then I actually ran a topographic survey, a full topo survey with my total station. We generated the point cloud on Pix 4D Catch, and I was able to actually use their snapping feature, which adjusts your data set right after you finish it to ensure that it closes on where you started by using some matching of the tie points. The Civil 3D model looked good. If you take a look at the contour lines, they were matching, so that told me that relatively speaking, my model looked good. And so what do the results look like? Well, let's go back to the iPhone 12 Pro. I used 2 of the points to align my data set to the total station so that I had some commonality when I would compare points. So I omitted points 102 and 107. By omitting those points, I came up with between some areas were a centimeter. I had one spot that was 20 centimeters, but in my mind, I was like, I'm getting centimeter level accuracy. I'm pretty happy with this. The following year, I did the same process, right? I just selected a couple of points, rotated my point cloud to match the total station data, and then measured the relative accuracy. I noticed that the accuracy was a little better here. We reached 7 centimeters in some spots, 9 centimeters in one spot, but the majority of these points were within 2 to 3 centimeters. For an iPhone, I felt that was pretty good. Okay, but now let's talk about a long linear path. iPhone 14 Pro in 2022 started measuring these points, and I found, again, I'm within 3 to 4 centimeters. So it's very similar to what we had the year prior, but now I'm actually really putting it to the test. I'm really making it travel a longer distance. When I reconstructed the data of the playground, I measured the absolute accuracy. And I found that the iPhone 14 Pro had an absolute accuracy of 1.46 meters, whereas the iPhone 13 Pro had 3.75 meters. I repeated this multiple times and had very similar results. So I found that the absolute accuracy was actually slightly better. If I were to guess, I would say the trajectory data was probably better because the GNSS was better. iPhone 15 Pro, we measured that island. You can see I have two surfaces on the bottom here, and one is from the total station, one is from the iPhone. They matched a volumetric measurement of about 10%. Okay, not terrible. It's good for doing volume work. And then the linear accuracy was between 2 and 3 centimeters. So pretty consistent now from what we've gotten from years prior. We also compared the 14 and 15 Pro. We found that both devices were about 5 meters of range. So the range was about the same. Didn't really change between those two. However, the density of the iPhone 15 Pro was greater. And once you got to 5 meters, you start to really see the structure deform with the 14 Pro versus the 15 Pro. The iPhone 16 Pro, I did run a relative accuracy assessment on it, as well as absolute. Again, 2 to 3 centimeters in the relative, and about, I think we said, where was it? Oh, I don't have it written here. Oh, no, I do have it right here. In some areas, it was 10 to 20 centimeters, but the worst of it, which is from one extreme to the other, was a little over 1.3 meters. Again, this is an iPhone. This is a $1,000 device, and it's doing pretty good. We ran a couple of special experiments, just things to test out. The first was attaching RTK to the iPhone to see if we can improve the trajectory data in order to improve the overall accuracy. So we did, again, a sloped measurement. This was a deep decline in Ohio State's campus. We measured it with a total station. We scanned it, and we found the accuracies were, this is absolute accuracy, not relative accuracy, within 0.3 to 3 centimeters. So absolute accuracy is definitely more valuable if you're trying to georeference your data set. However, the relative accuracy didn't really change much, which tells us the LiDAR sensor performed the same regardless of the trajectory data being higher accuracy. A few years later, Pix4D reaches out and says, hey, we've opened up our network. We are using a lot of other GNSS receivers, and we want you to kind of play around with adding data to an existing point cloud. So I went and scanned a new construction on a site that had been developed, and we have this site right here. Now I'm able to add this data in pretty accurately. We don't have numbers here, but I just think visually it looks very nice. Another thing I was able to do is take a utility drawing, digitize it into Civil 3D, upload that to Pix4D Cloud, and then use AR to actually see the utilities out in the field. So again, some special experiments we did, some fun stuff that we did. I thought this was really interesting just because I do a lot of utility work myself. And the last fun project I did was I put my iPhone on an electric scooter, and then I ran 2 ground truthing systems, one with a GNSS receiver and one with a prism on a total station. And the idea was that I would drive the scooter, one at 10 kilometers, one at 20 kilometers, and one at 30 kilometers an hour, and see how well I can collect data and test the trajectory estimation accuracy. So here's me on the top with the GNSS receiver as a ground truth, and on the bottom with a total station as the ground truth. Again, the GNSS receiver is a GS18I. It has an IMU in it, and then the total station is just being tracked by the prism is being tracked by the total station. So the trajectory estimations, this is the GNSS receiver, was pretty good, actually, at 10 kilometers an hour. It only struggled when it was near the trees. Down at the bottom is 20 kilometers an hour. You can see there's more struggle, especially when we would go under the trees. You saw that environment. It's a pretty urban and mixed environment. Total station held on pretty strong. Only one area in the 20 kilometer an hour section where it actually struggled. 30 kilometers an hour is where we saw some major problems. This is the GNSS receiver's trajectory estimations. Again, it's all over the place. It's not doing that great compared to what the iPhone measured. And this is the total station. It actually but like lost lock for a majority of the scooter ride. So I estimated that, if you go between 10 and 20 kilometers an hour, you should be able to map out pretty accurately. And then we did a point cloud analysis of the data sets that we collected, again, between 1 and 2 10 and 20 kilometers an hour, we were fine. At 30 kilometers an hour, we were just completely off. So what's next? Well, we anticipate the new iPhone, whatever they call it, probably 17, will have more integration with external IMU software or hardware. We want to start using terrestrial laser scanners. This was something I wanted to do for this presentation, but we didn't have the time to do it. But we anticipate to do more sensors using terrestrial scanners to do the ground truthing. And a plethora of other things that we want to do in order to improve these experiments through the years. So if you'd like to learn more about surveying, you can check out my YouTube channel. You can check out thesurveyschool.com. And I thank the organizers for having us here and joining us. And thank you for listening.
Rami, great job, great job.
Appreciate it.
Great job. So we've got actually, once again, a lot of questions coming in from Renata and others. So let's bring them up on screen and let's start with the first one. I would merge the first two, first two. So the first one, how close are we to using iPhones for serious site documentation? Are they good enough?
So this is my opinion. I think iPhone mapping in general is a good supplement to other types of terrestrial scanning. I don't see it taking over traditional scanning. I don't see it, being a replacement for surveying. But I do see it as a supplement. I do see it as us being able to fill in the gaps. This is something that's happening today with RTK technology, with higher-end IMU sensors. It's a matter of just having them integrated into our phones now.
Got it. Next one from Ivan. Do you think that mobile or wearable devices will replace all surveying tools used for 3D scanning in the future, in the near future?
I do not.
You don't think so?
No.
So as you said, like complements.
It will complement, yes.
Cool. Let's take one more. One from Nina. Have you also considered extending this experiment to other mobile phones with similar sensors?
We
so
should.
Not just iPhone.
I would love to try other sensors, other phones. There are many phones that are banned in the U.S. that I can't try, but there has been a huge jump in increased quality of sensors. They're getting a lot cheaper, so they're adding them into our smartphones. And quite frankly, if you have a good sensor in your phone, you should try to use it for mapping and see how it goes. That's part of the surveying process.
Rami, thank you so much.
Appreciate it.
Yeah, absolutely. Give him one more round of applause, ladies and gentlemen.